on the closed interval AB and differentiable on the open interval AB. Okay, so now you have the statement. If it turns out that f of A equals f of B, then there exists. That's the symbol for there exists. Then there exists our C value. Then how about we just say there exists C in the open interval AB such that f prime of C is 0. Okay, what this is saying is make believe here is A and here is B. F of A is the same height as f of B. Now, if the graph was told that f of x is continuous, that means when I go from A to B, when I go from this point to this point, I cannot lift my marker. Okay? And if it's differentiable, that means no corner points. Okay? So, it's a nice smooth curve. Now, what Rolle's theorem is saying is that there exists, I'm just going to change the wording. There exists at least one C in the interval where the derivative is 0. And here it is. Derivative is 0. In fact, it happens to be the same slope as the line that goes from f of A to f of B. It happens to be the slope of the line that goes from here to there, which will always be 0 because they both have no change in y. The slope is a change in y over the change in x. Here. If you go from A to B and you draw it without lifting your pen, that means it's continuous, and you have no corner points, you're going to have a C value. And you might have many, many C values. Here's A, here's B. You can have many C values. Here the derivative is 0, here it's 0, here it's 0, here it's 0, and there it's 0. Now, I guess I should bother to show that this may not be true if it has the derivative, say, doesn't exist somewhere in AB. For example, AB, here's f of A, here's f of B. The graph has a corner point right there. Notice, no tangent line between A and B is ever 0. The derivative is never 0. Well, it does look like it's 0 getting towards A, so why don't we fix that? Why don't we fix that? Let's make it so it's kind of clear that there is none. Here. Here. Okay? From here to here. Same f of A equals f of B. There's no place where the derivative is 0. If the slope of this line is 1, every point on this portion, the derivative is 1. If the slope here is negative 0.9, everywhere on there, the derivative is negative 0.9. And there, it's never 0. Okay, so this graph doesn't obey Rolle's theorem. Now, if a graph doesn't obey the criteria for Rolle's theorem, does that mean that it cannot be this magical C? The answer is that yes, it can happen. For example, right here, the slope is 0. But then I'll go and have a corner point. I'll even have 2 corner points. Rolle's theorem did not guarantee that C value. Rolle's theorem does not guarantee it. Now, because it's not differentiable. What if it's not continuous? What if it's not continuous? I mean, the classic case for it not being continuous, the simplest case, is as follows. Just remove that point. I mean, here's A and F of A and F of B. Here's the graph. But I'm going to go and be mean and remove that point right there. I'm going to remove that point. It's not continuous. Okay, nowhere is the derivative 0. On the left, I could have, here's F of A, and here's F of B. Graph goes like that. It comes down here, and it's a straight line, open there, and then from here, it comes down like that. Nowhere is there a derivative 0. Let me be clear that I'm not touching that point. Nowhere is the derivative 0. If the graph is not continuous, it might fail. Okay, it might fail. So I'm going to give you some functions, and you're going to have to decide if Rolle's theorem guarantees the C value, and if it does, find it. Suppose you have the following problem. F of x is equal to x squared minus 2x. And the interval is, say, from 0 to 2. Now, this here is a polynomial, and it's always continuous on its interval, on a closed interval. So, criteria 1. F of x is continuous on a closed interval. If the interval was open, if this interval was open, say 0, 2, that one, or one endpoint was open, or maybe 0 is included but not 2. It's not closed. All those 3 intervals are not closed. Okay, but our interval is closed. That is, if you had one of these, you can say immediately it doesn't apply to Rolle's theorem. The question is does this function and interval satisfy the conditions of Rolle's theorem? That's question 1. Question 2 is, if it does, find all the C values. Okay, polynomials are continuous. I meant to say differentiable. F of x is differentiable on the open interval 0, 2. Now, condition number 3. F of the left endpoint must equal f of the right endpoint. The left endpoint is A and the right endpoint is B. F of A must equal f of B. Well, f of 0 is 0 squared minus 2 times 0, which is 0. And f of 2 is 2 squared, which is 4, minus 2 times 2, which is 4. And 4 minus 4 is 0. So Since these are both equal, we satisfy condition number 3. Now, and only now, do we bother to find the C value. We want f prime of x, which is 2x minus 2. We want, now, it does not equal 0. Students put that down, I take points off. F prime of x does not equal 0. We want to set f prime of x equal to 0. Well, if this takes away that equals 0, then these two things are equal to one another. Boom, they're equal. Just jump on it. 2 times x. X I like to call some number. 2 times some number equals 2. That number is 1. So I was about to say that's the answer. The answer is to let c equal 1, or to choose c equal 1. And notice that 1 is in between our intervals. Now, if the derivative was more than a linear equation, if the derivative was a 5th-degree equation, you might get 5 zeros. Not all of them will be between 0 and 2. So don't let c equal those c values that are not in between 0 and 2. Okay, let's try another one. And you have to state, yes, f of x is continuous, possibly because it's their polynomial. Yes, it's differentiable. How about this problem right here? F of x is equal to x squared minus 1 over x on negative 1, 1. On the closed interval, negative 1, 1. Now you have to state why it's continuous. Why is it continuous? Well, since f for 0 is 0 squared minus 1 over 0, which is 0 minus 1 over 0, which is negative 1 over 0, which does not exist. And this is key. And 0 is in our interval. Then f of x is not continuous. Is not continuous on negative 1, 1. It's discontinuous at 0. It doesn't exist. Whatever the graph looks like, I assure you, it does not cross out any point in red. It does not. Maybe it goes like this, crosses the y-axis, it turns out, and then continues on. Maybe that's between negative 1 and 1. But it's not continuous at 0. This problem is done. Okay, so you should say this is not a Rolle theorem problem. This problem does not meet the criteria of Rolle theorem. Does that mean that there won't be a derivative that equals 0 between negative 1 and 1? Maybe. I don't know. I don't even care, because Rolle theorem doesn't guarantee it. It must satisfy the 3 conditions. You have to know the 3 conditions. Suppose I tell you that f of x is equal to x squared minus 2x minus 3 over x plus 2, and we're going from negative 1 to 3. And let me write it down very clearly. A fraction, a rational function, that means that it's a division. A rational function is discontinuous where it's not defined. F of x is not well defined at x equals -2. This makes the bottom 0. That is, f of x is discontinuous at x equals -2. Oh, that is not in our integral, sorry. I was thinking positive 2. Okay, so the only place the f of x is not well defined only at x equals -2. Okay, that is f of x is continuous on the interval -1, 3. A rational function, one polynomial divided by another polynomial, is only discontinuous where the denominator is 0. It's only discontinuous or not well defined, which means discontinuous, where the denominator is 0. If the numerator and the denominator are polynomials, it's discontinuous only where the denominator is 0, which is -2. But -2 is not in our interval. So criteria 1 has been met. F of x is continuous. Now they want to know about differentiability. What I might do is I would try to see if I can factor f of x. So let's write it down. And if this doesn't simplify things, then we use the quotient rule. Since it's x squared and not 7x squared or -3x squared, we play the x followed by a number game times x followed by a number game. I want two numbers that multiply up to -3 that add up to -2. The only numbers I'm familiar with that multiply to -3 is 1 and -3 and 3 and -2. Well, that's not true. 3 and -1. 3 and -1. The first pair, the winner, they add up to -2. Okay, so the 1 is understood to be +1. I have +1 -3. What I was hoping was, to be honest, is that one of these would have been x plus 2, so I could have crossed them out. So it was worth a try. It didn't help. It really would have saved us time, but in the end, it cost us a little time. So let's get rid of it to say void space. And now let's take the derivative. Okay. So, derivative of f of x. It's the derivative of the top. It's 2x minus 2 times the bottom. Now I reverse the game. Minus. We keep the top the same way. We take the derivative of the bottom, which is 1. And all of this gets divided by the bottom square. X plus 2 squared. So we're going to have 2x squared plus 4x minus 2x. 4x minus 2x is 2x minus 4. And we are going to take away x squared minus 2x minus 3. Multiplying by 1 doesn't do anything. And all of this is over x plus 2 squared. We have 2x squared, and here we have x squared. And we are subtracting. So now we only have 1x squared. Here we have plus 2x. Here we have minus 2x. We're subtracting. That gives us 4x. Here we have minus 4 or -4, and here we have -3, and we're subtracting. That gives us -1. And all of this is divided by x plus 2 squared. Now, where 2 says it's differentiable on the open interval 1 to 3. Where is this fraction not differentiable? Well, it's not differentiable where it's not defined. A fraction is not defined when the denominator is 0. Okay, so A equals does not exist only at x equals negative 2. So negative 2 is not in, that's what that symbol means, it's not in negative 1, 3. So f prime of x is differentiable on negative 1, 3. So condition 2 has been met. So now we have to look at condition 3. One might argue condition 3 is the easiest one to check, so maybe you check it first. Nothing wrong with that. Okay, condition 3 says f of the endpoints are equal. F of negative 1, this is how I write x. X squared minus 2 times x minus 3 over x plus 2. The bottom is 1, and dividing by 1 doesn't do anything. So we have negative 1 squared, which is 1, minus 2 times negative 1, that's plus 2, minus 3, which is 0. And after 3 is 3 squared is x squared minus 2 times x minus 3 over 3 or x plus 2. So it's 9 minus 6, which is 3. Minus 3 is 0 over 5, which is 0. Okay, they don't both have to be 0. They just have to be equal. Now, some textbooks say they have to be equal. Now, I'm unclear why they bother to say that. Unless centuries ago, Rolle's theorem really stated that. But they don't have to be equal to 0. They have to be equal to one another. So, Rolle's theorem has been satisfied. Okay, now we take the derivative, which I think is a little bit depressing because I think we already did it. I erased it. Okay, so unfortunately we have to do the derivative again. Derivative of the top times the bottom minus just the top times the derivative of the bottom, which is 1, which I don't need to even denote. And this all gets divided by whatever the denominator is, quantity squared. So you have 2x squared plus 4x minus 2x is 2x minus 4. And from there, you are going to take away an x squared. You're going to take away a negative 2x. You're going to take away a negative 3. And that all gets divided by x plus 2 squared. So you have x squared plus 4x minus 1 over x plus 2 squared. And this does not, okay, so now, not the friendliest polynomial. So now, you want to set it equal to 0. You want to set it equal to 0. That is, you want the numerator equal to 0. Now, since it is x squared, we'll try to factor it. But I can't think of two numbers that multiply out to negative 1 that add up to 4. Okay, so, Oh, why am I doing that? Because I want to know when the numerator is 0. Because if the fraction equals 0, it's when the numerator is. So I guess we're stuck using the quadratic formula. A is the number in front of x squared, which is understood to be 1. B is the number in front of x, including the sign. And C is just the constant. So we have x is equal to negative b, 4, plus or minus b squared minus 4 times a, which is 1, times c, which is negative 1. And all of this gets divided by 2 times a, which is 1. So we get negative 4 plus or minus 16 plus 4 over 2, which is negative 4 plus or minus the square root of 20 over 2. And we'll think of 20 as 4 times 5. So the square root of 20 is the square root of 4 times the square root of 5 over 2. And this is negative 4 over 2 plus or minus. Now the square root of 4 is 2, radical 5. And that also gets divided by 2. This goes in here negative 2 times, plus or minus. This goes in here radical 5 times. Now, this here represents two numbers. One with the plus sign and one with the minus sign. Well, negative 2 is not in our interval. So if you take away more, like square root of 5, it won't be there. Okay, this will be below negative 2. That's not between negative 1 and 2. Now, we need to look at the other number. And this definitely should not be done with the calculator. Okay, we should learn how to start figuring things out. Okay. The square root of 5. So the largest number below 5 that I know the square root of is 4. So, and the square root of 4 equals 2. The square root of 5 is less than 2. The smallest number above 5 that I know the square root of is 9. And that equals 3. That is, the square root of 5 is jammed in between 2 and 3. And we want to take away 2. We want to take away 2. This is 0. In the middle, we have negative 2 plus the square root of 5. And this is 1. That is, this number is in between 0 and 1. But that's in between our interval. That's in between negative 1 and 3. So there is your C value. There is your C value. That's Rolle's theorem. I just really quickly want to show you that you don't have to have f of A and f of B both equal to 0. Because let's suppose you do. Here's the x-axis. This is A, this is B, that's f of A, this is f of A, and that's f of B. Rolle's theorem says if you go from A to B and it's differentiable and continuous, there must be a C value. Here it is. Well, you know what? If I raise this graph up, so let's call this y equal f of x. If I raise this graph up by 3, say there's the y-axis, I'm going to draw f of x plus 3. Because I'm just going to bring it up 3. So, here is 3. Same A, same B. Same graph, except I brought it up 3 units. Of course I'm going to have the same answer. I'm going to get the same answer. I'm going to get exactly the same C value. Okay, the picture is the same. The only thing that's different is the x-axis, where it is. If I erase the x-axis, the two graphs look the same. They both look like this, the same exact graph. Okay, now we move on to the mean value theorem. The mean value theorem is just a tilt of the Rolle theorem. It's just tilt and Rolle theorem. For example, Rolle theorem says, let me not do that. Rolle theorem says the following. It says if you have 2 points where they both happen to have the same y value, if you draw a smooth differentiable curve, somewhere in the middle, the slope will be 0. That is, it will equal the slope of the line that connects f of A and f of B. The derivative equals the slope of the line that connects A and B. Well, what if A and B, f of A and f of B, are not the same y value? Suppose f and A and f of B are different y values. So here's the line that connects f of A and f of B. And suppose the graph goes like that. Suppose the graph goes like that. Well, somewhere between f of A and f of B, somewhere between A and B, there must be a value, or C value, where the derivative has the same slope as this line. All I did was take this picture and rotate it. Just look at it sideways a little bit. Okay. Now, what exactly is this saying? So, let's give it the appropriate heading. Mean value theorem. Mean value theorem. The initial conditions are the same. F of x, except the third one. First two conditions are the same. F of x is continuous on the closed interval from A to B. Condition 2, f of x is differentiable on the open interval AB. If those two conditions are met, then there is a C, where the slope of this line is equal to the derivative at C. Now, what is the slope of this line? Well, let's give it a y-axis. This point, and the name of the function is f of x. So then, this y value, if this is A, here's a point on the graph, that's f of A. And here's B, there's the point on the graph, this here is f of B. And basically, I'm getting this right triangle. I'm getting this right triangle right here. And I want to know the slope of the line that goes between those 2 points. Well, the slope of any line is the change in y to the change in x. But it turns out that this distance here is the same as this distance, which is f of b minus f of a. And this distance here is the same as this distance, which is b minus a. So f of b minus f of a over b minus a. That number, that slope, that's the slope of this line. It's a number. It's the same as f prime at some c value. There's the c value. The c must be between a and b. Okay, this here is pretty much Rolle. F of x f of x is differentiable on the open interval AB. That's it. Then there exists a c in the open interval AB such that this box formula is true. Okay, that's all. That's the mean value theorem. So basically, if you think about it, you never even have to mention Rolle's theorem. Rolle's theorem is just a special case of the mean value theorem. What's special? Oh, f of a equals f of b. So suppose you're given f of x is equal to x squared on the interval -2, 1. Now, you need to say it. Since f of x is a polynomial, then it is continuous on -2, 1. Number 2, since f of x is a polynomial, then it is differentiable on that open interval. You have to state that. Now, and only now, can we talk about Rolle's theorem. We need to do f of b, f of c, minus f of a, over b minus a. That is, remember, a, b. We need to do f of 1, f of minus 2, over 1 minus -2. F of 1, just square what's in the bracket, get 1, minus, square what's in f of that number, we square it, -4. The bottom is 3. So you get -3 over 3, which is -1. I want this to equal f for some c value. Excuse me, f prime of the c value. So f prime of x is equal to 2x. So f prime of c is 2c. And you want this to be -1. You want it to be -1. So divide by 2, and you get c is -0.5. And you really should verify that -0.5 is in between -2 and 1. And of course it is. If either of the first two conditions are not met, you say Rolle's theorem does not guarantee, the mean value theorem does not guarantee the c value. Let's try another one. Suppose f of x is x over x plus 1 on the interval, probably like -0.5 to 2. -0.5 to 2. Okay. Now, this here is a rational function. The numerator is a polynomial, and the denominator is a polynomial. So you should say f of x is a rational function. Rational functions are only discontinuous when their denominator equals 0. Our denominator equals 0 when x is -1. -1 plus 1 is 0. Since negative 1 is not in that interval, hence f of x is continuous on the interval negative 1/2 to 2. You need to state all that. Number 2. Let's find out if it's differentiable. Subtraction, quotient rule. The derivative of the top, which is 1, times the bottom, minus the top times the derivative of the bottom, over the bottom square. 1 times x plus 1 is x plus 1, minus 1 x times 1 is x, over x plus 1 squared. X minus x is gone, so you just get 1 over x plus 1 squared, which does not exist only when the denominator is 0. It does not exist in negative 1. And negative 1 is not in our interval. Hence, f prime of x is differentiable on negative 1/2 to 2. So this is our mean value theorem problem. Where are we? We are not going to lose the derivative this time. This here is the derivative. Okay, that is the derivative. Alright, so now we need to find f for b minus f for a over b minus a. We need to find f for 2 minus f for negative 1/2 over 2 minus negative 1/2. F for 2 is, f of anything is anything divided by 1 more. 2 over 1 more. X plus 1 is 1 more than x. Minus, you have 1/2 over 1 more. 1 more than 1/2 is 1/2. And in the bottom, you have 2 1/2. So you have 2/3 minus 1. 2/3 minus 3/3 is negative 1/3. In the bottom, 2 1/2 is 5/2. So when you divide these two numbers, it's the same as this. No, it's not. It's the same as negative 1/3 times 2/5 times 2/5 minus some silly error. We get negative 2 over 15. And we want f prime of c, which is, since this is f of x, then f for c is just 1 over c plus 1 squared. We want this to equal to negative 2 over 15. That's what we want. Okay, so we need to find that c value that will do this. Now, since the variable is in the denominator, c is in the denominator, I'm going to take the reciprocal of both sides, especially since the numerator is 1. If I flip this over, I get c plus 1 squared. If I flip this over, I get negative 15 over 2. And then I wonder why this is not working. I see why it's not working. Right here, shucks. Right there. I didn't put down the correct x value. The numerator is x. It should have been negative 1/2. So this really becomes 2/3 plus 1, which is what? 5/3. So I don't think it's a disaster what happened. Why do I say that something went wrong? Because nothing squared is ever a negative number. So this becomes 2/3 plus 1, which is 5/3 over 5/2. If you do the math, you get 2/3. You get 2/3. So I'm going to replace the derivative. I'm going to state the derivative should equal 2/3. Should equal 2/3. So when you take the reciprocal of the left side, you get c plus 1 squared. Take the derivative of the right side, you get 3 over 2. Take the square root of both sides. What do you square to get 3 over 2? Plus or minus the square root of 3 over 2. So c plus 1 can equal radical 3 over 2, or c plus 1 can equal negative radical 3 over 2. Take away 1, you get c is equal to negative 1 plus the square root of 3 over 2. Take away, the whole thing's under the radical. Take away 1, you get c is negative 1 minus the square root of 3 over 2. Okay. So the question is, where are these numbers between? Well, if you take away 1 and then you take away more, you'll be below negative 1. Here is negative 1/2. Here is 2. You're supposed to be in here. Negative 1 is right here. If you take away more, if you take away a little, if you take away a lot, if you take away more, you won't be in between negative 1 and 2. Negative 1/2 and 2. So this one is rejected, which means the other one will be there. But let us convince ourselves of that. Let us be very rigorous about it. So we're going to play that game that we played in the last problem. We're going to play the game that we played in the last problem. The square root is 3 over 2. 3 over 2 is 1/2. What are the numbers right around 1/2 that you know the square root of? Well, you know the square root of 1, which is 1. The largest number below 1/2 that you know the square root of is 1. The smallest number above 1/2 that you know the square root of is 4. Square root of 4 is 2. That is, the square root of 3 over 2 is jammed in between 1 and 2. So we want to now take away 1. We want to now take away 1. So negative 1 plus the square root of 3 over 2 is in between 0 and 1. But if you're in between 0 and 1, then you're in between negative 1/2 and 2. Why is that? Because if I'm thinking of a number in between 0 and 1, well, certainly that number is also in between 1/2 and 2. So there is your c value. C is equal to negative 1 plus the square root of 3 over 2. Okay. Do not give up on doing those first 2 steps. You have to verify that it's a Rolle theorem, a mean value theorem problem. How about one last one? Suppose I tell you that f of x is equal to x to the 2/3 on the interval 0, 1. 0, 1. Now, how I would state number 1 is need to show that the limit, if you can show that the limit as x goes to c of f of x is equal to f of c, then you're done. That's what you want to show. Well, the limit as x goes, now recall this theorem. Recall this theorem that says that if you have a polynomial to a power, say n, you can take the limit of that polynomial and then raise it to the nth power. For example, somebody asks you what's the limit as x goes to 2 of x plus 3 to the 10th power. That means fine. We would say 2 plus 3 is 5, and the answer is whatever 5 to the 10th is. But what the theorem is stating is you can take the limit as x goes to 2 of x plus 3, which is 5, and then raise that to the 10th power. Okay, so we have x to the 2/3. This is the same as the limit as x goes to c of x, and that gets raised to the 2/3. But this limit is simple, it's just x. As x goes to c, x goes to c, to the 2/3. But that is f for c. And we didn't even say it's between 0 and 1. This is true for all x. Okay, that's the symbol for all. Well, that doesn't look so well. For all x, that's true. So, now remember, so f of x is continuous for all x, in particular on 0, 1. That was a tricky one. I had to think about that one for a couple of seconds, which means you have to think about it for maybe 10 minutes. But you can do it. Okay. Number 2, differentiable. F prime of x is round the power, make the new power 1 less. Subtract. Top minus bottom is -1 over the same denominator. So this is 2 over 3x to the 1/3, which does not exist only when x is 0. Now you have to be flipped. So f prime of x is differentiable on that open interval, 0, 1. Whatever AB is, we must be continuous on open AB. But 0 is not in 0, 1. So condition 2 has been met. You satisfy condition 2. Okay, and that's the only 2 conditions you have to verify for Rolle's theorem. Now we need to find that c value. I'm not going to erase the derivative. So f for b minus f for a over b minus a, which is f for 1 minus f for 0 over 1 minus 0. We have 1 to the 2/3 minus 0 to the 2/3 over 1 minus 0. Well, 1 to any power is 1, and 0 to any power other than 0 is 0. So 1 minus 0 is 1, 1 minus 0 is 1, we get 1. So we want the derivative at c to equal 1. That's the derivative equal 1. Okay. Take the reciprocal, hit C in the top. 3C, or just say this times this, which is 3C to the 1/3, equals the top, which is 2. Divide by 3 now. C to the 1/3 is 2/3. Now, cube both sides. Cube them. Because when you cube the left side, you get C. And when you cube the right side, you get 2 cubed over 3 cubed. Now, this number is more than 0, and it's less than 1. It's more than 0 because it's positive. It's less than 1 because the bottom is bigger than the top. Bingo! It's between 0 and 1. There is your C value that Rolle theorem guaranteed that you have. This was a brutal problem, but you have to be able to handle it. It might be on your test. Okay, that completes the section on the Rolle theorem and the mean value theorem. Good luck with it.